first of all, this one here, is that an inverting or a non-inverting Schmitt trigger?
Inverting.
It's inverting, yeah. And it's easy to mix them up because the difference between the two is only these two things swapped around. The way to identify it would be to look at V in. If it's going into the inverting input, it's inverting. So it's an inverting. You're writing in some crayon.
Joe, does it depend what V in goes into?
Yeah. So here, V in goes into inverting.
If it was in the bottom one, it would.
Yeah, what happened is it would be V in would be here,
Yeah.
and the V ref would be up there. And you just swap them over, the circuit's the same. So that's why it gets a bit confusing. So it says calculate the value of V in, which causes V out to change from plus 12. So you write the plus 12 on here, plus 12 volts to minus 12 volts. So we don't need to think about that. We need to just say, right, what is the voltage at X? Because basically these two voltages here are the same at the switching threshold. So to work out what the value of V in needs to be to force this to flick to minus 12 volts, we just have to know what the voltage at X is. Okay? So at that switching voltage, V in is the same as X. No current at all flows into an op-amp because they've got a high input impedance. So therefore, we just really need to work out the voltage here at X. Now, there's a number of ways you can do that. You can do it using potential divider equation. But actually, if you just use it doing Ohm's law, you can keep it pretty simple. What we need to do is calculate the current flowing through these resistors. Once we've worked out the current going through the resistors, we can use Ohm's law to work out the voltage across each or one of the resistors. Once we've established the voltage across one of the resistors, particularly this one, we can then look at the voltage here and see what voltage at X is going to be in relation to that. Okay, we'll do that. So, to work out the current, we need to know the voltage across these two resistors, which is 12 minus 3 divided by 20 plus 30. And that's going to give us the current. So we need a calculator. I don't know what a calculator. I can bash that in for me. Go on, do you want to bash them in for me? 12 by, so 9 divided by 50.
0.18.
So we've got 0.18. Okay? Alright, 0.18. Oh, it's milliamps, sorry. Thought that seemed a bit high. It's milliamps because we've left them in kiloohms. So if you leave them in kiloohms, your answer will come out in milliamps. So now we can say, right, jolly good, we've got 0.18 milliamps flowing this way from plus 12 down to 3 volts there. None of it is going into X. So if we want to work out the voltage across R2, we can just do V equals the current multiplied by the value of R2. So V equals 0.18 multiplied by 20. Okay? Now, because that's milliamps and this is kiloohms, we can actually leave that like that, which equals that 3.6 volts.
Yeah.
Okay, is that the answer? Is that the voltage here?
That's the voltage across R2.
Yes, it's the voltage across R2. Now the voltage is on its way up because it's got to get to 12. So what's the voltage at X going to be?
6.6 then?
Yeah, 6.6.
Why do you do 20 plus 30?
Because we've worked out the total current, so it's in series, so it's that.
Oh, so
plus
it's
that.
the total current across the whole thing?
Yeah, we're working out the current going here. None of it can go there, so it's got to go through that resistor as well. So therefore we've got 3.6. So now hang on, just put this on. So X equals 3 plus 3.6, which equals 6.6 volts. Okay? Right, now we've got to do it the other way. So I shall change colour. Ooh. The high techness of it all. So we can make that minus 12. Saturating, it did say plus or minus 12. Just careful, it's not always plus or minus the same value. It could be 10 and 0, has been in the past.
So now there's 15 volts across the resistors, right?
Yeah, so now, that's right, we've now got 15 volts across the resistors rather than 12. So, some of it, if you look at, some people get worried about the negatives and things in this, but you just think about the difference being 15 volts. But this time now it's kind of going down that way, isn't it? Current this time is going to be going that way because it's going from 3 down to minus 12. So this time we've got 12 plus 3, so 15 over 50. You do that one? Is that 0.3? So that's 0.3. My amazing mental arithmetic. It says not. Oh, it's a primary school and they didn't bother teaching it, so I'm not really worse than yours. 0.3 milliamps. So what do we do next? We now know the current is 0.3 going that way.
Is it the same as one before?
Yeah. So this time we're just going to multiply that by that. So we do 0.3 times 20. And when you get quick at these, you can just do that in one stage. Do that and then multiply it by 20.
Yeah.
You know, but anyway, do 0.3 times 20, which equals 6 volts, isn't it?
Mm-hmm.
So we now know that there's 6 volts across that resistor. And now we have to think, what is the voltage at X?
9.
Well, careful, because that would be going up to 9 and then all the way back down to minus 12 there. Can't be happening. It's going down, 3, down, 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 down to minus 12. Yeah, so it's got to be 6 volts less than 3. So V in equals 3 minus 6, which equals minus 3 volts. So you've got your two switching thresholds, one at plus 6.6 and one at minus 3. Sound? Should we do a non-inverting now? What difference would it make if this was 0?
That means it'd be like plus and minus the switching threshold.
Yeah, we'll recall that if they're both equal.
Symmetrical.
Good. So if that was equal, sorry, if that was 0, then it would be symmetrical. That would mean that you would only have to do the calculation once and it'd be plus and minus that value. Whereas if you do it twice, you're just wasting your time. And then you'll find it's the same.
What if the
Sander, do you know
R
what to watch
is
this?
the
Are you alright with it?
I struggle with everything, so let's focus on
That's just a really inefficient way of doing things. Right, so now, now we've got a non-inverting, haven't we? So this is now a non-inverting. And you can see why it gets a bit confusing because they're similar but different, so you can quite easily mess them up. So now we've got this one saturates at plus or minus 10 volts. Sandy, you might as well watch this when it goes through. It's silly explaining it. Right, so we've got here, what could we do with the value of X then? Do you reckon, Alex? You have these nailed, haven't you? What's X? What's the voltage at X when it switches? Expert?
Is it? Do you not subtract the reference voltage?
No! Anyone else?
V in?
No?
Like there's one at the top.
Yeah, this one, the reference voltage. This is the reference, okay? What did I say just before? When they switch, these two inputs are the same, aren't they? Yeah? So therefore, X must be 1 volt. And if you don't get that, then you can't answer the question, can you? Because you'll go do whatever you can and you'll never answer the question. Because what you're trying to find out is what voltage here would give you 1 volt there and the voltage, saturation voltage there. Okay? So this time, we've labelled that 1 volt and we're looking for that one. So this time, the only thing we can do is to look across This one, right? We've only got a single resistor this time. We can't do that because we don't know the value of that voltage. So we've got to do that to that. So this time we can say, I'm not answering this question by the way, I'm working out the switching threshold. It's a different question.
Isn't the switching threshold on the same? Are they the same?
That and that are the same, yeah.
Oh,
But well, that's not the friction threshold, that's this voltage here.
okay.
Okay? So we need to find out, first of all, the current through this resistor, which we can do using Ohm's law. Then we can assume, because no current flows through that the same current flows through this resistor, so we can use Ohm's law again to work out the voltage across this resistor. Once we know the voltage across that resistor, we can take it away from 1 and you'll get the voltage there. So we can do 10 minus 1 to get the voltage across that resistor, divided by 30, which equals
0.3 milliamp.
0.3 of a milliamp, thank you. So we can then, we know the current there is 0.3 of a milliamp, so it's 0.3 of a milliamp through that one. So we can do 0.3, multiply it by 15, and we'll get, is it 4.5?
Yeah, 4.5 milliamps.
4.5 volts.
Yeah, sorry.
4.5 volts. Still not the answer. If that's got 4.5 volts across it, what is the voltage going to be here?
Negative 3.5.
It's on its way down, isn't it? So we've got 1 here, and that must be 4.5 volts less than 1.
So just take negative.
Yeah, so you do V in equals 1 minus 4.5, which equals minus 3.5 volts. Okay?
And do it all again for the
Then
other.
you've got to do it all again for the other way. Yeah, exactly. I'll change the colour.
So you have to do it for the plus one as well.
Guys?
When would you not have to do it do it again?
When they're symmetrical, that's 0 volts.
Ah, that one's it. That's
So
right.
now we've got this one saturated at, say, minus 10 volts. So this time we've got minus 10 to 1. So this time we've got 11 volts divided by 30 times 15. What's that? 5.5 volts. See what I've done there? Shortcut. I've gone minus 10 to 1, which is 11. Divided it by that, 30, giving me the current. Multiply it by 15 to find the voltage across that resistor. Gives me 5.5 volts. So if we've got 5.5 volts across here, what's the voltage here going to be then?
6.5.
Yeah, because we've already got one, and it's on its way up. So therefore, V in equals 1 plus 5.5, which equals 6.5 volts. So that's your inverting and your non-inverting Schmitt trigger. Is there anything else? You get it? If you don't, we'll leave it there, shall we?